Hello everybody, my name is Maddalena Amendola and today I will present to you the paper Data Assimilation in the Latent Space of a Convolutional Autoencoder. My co-authors are Rossella Arcucci, Laetitia Mottet, Cesar Casas, Shiwei Christopher Payne, Paul Linden and Hike Guo from different universities, the Data Science Institute of the Imperial College, Department of Earth Science and Engineering, Imperial College, Department of Applied Mathematics and Theoretical Physics, University of Cambridge, and Department of Computer Science, Hong Kong. This work has been developed as part of the data learning working group, whose goal is to build new technologies by combining machine learning techniques and data assimilation techniques that are independent from the application, so the same technology can be applied to different problems of different nature. The project is part of the MAGIC project, whose goal is to study and implement systems to achieve the reduction of energy demand through natural ventilation. The question that usually arises in industrialized cities where there are high levels of pollution is whether it is possible to clean the air of an interior through natural ventilation. This question could be answered using computational fluid dynamic systems that are too slow. The goal of data assimilation is to improve the performance of a dynamic system. So in this case, in this image, we have the model that is our dynamic system. We also have observations that are real data coming from instruments like sensors. We know the model errors and the observation errors, and the data assimilation combines both observation and model in optimal way. One of the most used approaches of data assimilation is the Kalman filter, that is basically a prediction-correction cycle. In the prediction phase, we use a dynamic system to predict the state of the system for a given time step. In this case, we use the state of the system at time step k to compute the state of the system at time k plus 1. This is an a priori estimate, and it is used in the correction phase, where the Kalman filter combines it with the observation of the same time step k plus 1 to compute the a posteriori estimate that is again used in the prediction phase and so on. The problems we want to overcome are basically two. The first problem is that dynamical systems are based on computational fluid dynamics models, simulators, that consume a lot of time and computing resources. The second problem is that the background produced by the dynamic model is defined in a large computational grids that deals to a big data problem that usually is impossible to manage without introducing approximation or space reductions. The idea to overcome the first problem is to create a faster system on simulated data to emulate the dynamic models. So, to manage the big data problem, we can use reduced order modeling techniques that allow to reduce the physical space to speed up the dynamic model and the data assimilation process. One type of problem is the principal component analysis that is based on a truncated singular value decomposition analysis. The problem is that the accuracy of the solution shows a strong sensitivity for the variation of this parameter. So, an alternative are neural network, in particular autoencoder. Autoencoders are usually used for dimensionality reduction and feature learning. The autoencoder is composed of two parts, the encoder and the decoder. The encoder takes the input and, through some nonlinear transformation, computes the encoded version of the input. On the other hand, the decoder takes as the input the encoded version and always through some nonlinear transformation bring back the input to the physical space. The questions are two. Can we use Kalman filter in the latent space? What is the forecasting model in that case? This is the workflow of our model we call Latent Assimilation Model. The blue blocks are the autoencoder. The yellow block is the dynamic system that in this case is an LSTM, which is a recurrent neural network with good performance with time series data. And the green block is the Kalman filter that performs the simulation in the latent space. In this case, we want to predict the state of the system at time step k, so we need the state of the system at time step k minus 1. We pass this state to the encoder that computes the encoded version of the state of the system. Then we use the LSTM to predict the state of the system at time t, and it's always an encoded version. To perform the assimilation, we need the observation of the same time step, so we process it always through the encoder, and then the Kalman filter combines both the state of the system and the observation to compute the a posteriori estimate. To bring back the state of the system to the physical space, then we use the decoder. We use a special version of the Kalman filter that is called optimal interpolated Kalman filter, for which the covariance matrix is fixed. So this is our cycle, where in the prediction phase we use L, that is the function of our LSTM, to compute the state of the system at time t plus 1. Then in the correction phase we have Q, that is the error covariance matrix of our model, R, that is the error covariance matrix of the observations, H, that is the observation operator, and K is the computed Kalman matrix. This matrix is used then to combine the state of the system and the observation to compute the a posteriori value. L is our LSTM, that is a recurrent neural network composed of a forget gate, input gate, cell state, and output gate to decide what kind of information should pass. Here we will present you the data used and the experiment done. The model is applied to real data collected by MAGIC. Researchers collected measurements of outdoor and indoor air quality, the latter within a naturally ventilated room in the Clarence Centre of Southwark in London. In this room, there are 7 sensors at different positions and at different heights. The data was ready to be processed as needed, so we worked on it. Originally, the domain was this one that is a big unstructured 3D mesh, but we are only interested in this room, so we extracted this room. The data have been created using Fluidity, that is a fluid computational dynamics software. We have used a time series of 2,500 time steps, and as I already said, the data were 3D unstructured meshes, but we want to work with structured data. So we cut a slice of the room located halfway up to its height, and we create 2 datasets. The first dataset is a matrix of the dimension 250 per 180, and in each position of this matrix we can find the CO2 concentration. Then the second dataset is built converting these matrices into 3D RGB images. These are 6 different examples of our data, and as we can see, these are values of CO2 concentration, and the red color means high value of CO2 concentration. As I already said, there are 7 sensors located at different positions and at different heights in the room. So the first step was to look for the position of these sensors in our matrix, considering the size of the room and the size of the matrix. Then sensors provide CO2 concentration values within a certain radius. So we expand these values in a radius of 30 centimeters. Then, since we want to fill every position of our matrix, we perform a linear interpolation of this value, and this is the result. The data is a temporal sequence, and we decided to divide this sequence into three sets for training, validation, and testing. First of all, we remove from this sequence all time steps for which we have observation to perform the assimilation of real data. Then we decide to consider two consecutive time steps for training and then skip one position. Every skipped position is then assigned to validation and testing set. Now I will explain how we found the structure and the parameters of our models. Since we are working with grid data, we decided to use a convolutional autoencoder that takes into consideration also spatial information. We reduced the input size from 45,000 of points to a vector of 7 points. For the structure, we first experiment the number of layers in both encoder and decoder. We then tried to use the convolutional transpose in the decoder, and finally we tried to change the kernel size. This is the final structure of our autoencoder. Then, on this structure, we perform a grid search, changing the number of filters, activation functions, epochs, and batch size. The table shows the performance of autoencoder, the autoencoder for both datasets. We can see that they perform very similar. The same study is done for the LSTM. First of all, we studied the structure of the LSTM, trying to stack from 1 to 5 layers, but one layer of LSTM is enough for our task. Then we perform a grid search, changing the number of nears, activation functions, steps, epochs, and batch size. These are the results of the LSTM for both datasets, and this time the RGB dataset perform a little bit better. Now I will present you the result of our latent assimilation model. These are the mean square error for both datasets of our model without the assimilation. Instead, the table shows the result of our model with the assimilation of real data in the latent space. R is the error covariance matrix of the observations, and we compute R like a covariance matrix or like a diagonal matrix with small values in the diagonal, because in this way we trust more the real data coming from instrument. We can see that the assimilation of real data in the latent space always improve the performance of our model, and that it takes less than 1 second. Instead, these are the results of our model performing the assimilation of real data in the physical space, so working with big matrices. In this row, we have the result of this standard latent assimilation, and we can see that the assimilation of real data always improves the models, but that the latent assimilation model is better both in terms of accuracy and also in time. In conclusion, we can say that performing the simulation in the latent space can improve the prediction both in accuracy and time. And as a future work, we propose to adapt the latent assimilation model for 4D variational data assimilation method to test the methodology on a 3D space using a 3D convolutional autoencoder. developing latent assimilation with an encoder-decoder which works directly on a 3D adaptive and abstracted mesh. And finally, instead of using only indoor data, the methodology could be applied considering the exchange with the outdoor environment or tested in different applications. Thanks for your attention, and if you have any question, you can contact me with this email.